Okay. So in a previous example, we looked at being given a sort of general integral to do, and then we had a choice. Do we set it up with rectangular coordinates, or do we set it up with spherical coordinates? Okay. So in this one, we're going to look at something that's given, in a sense, that's given in rectangular, and we've got to convert. So I want to take a close look at that. And where the conversion is a little trickier. Okay, so here's this question. So let's calculate the triple integral over some solid b of this function, e to the x squared plus y squared plus z squared to the 3/2 dx dy dz. And b is the solid ball, radius 1, centered at the origin. Okay. So in order to do this integral, let's think about what's going on. So remember, there's three aspects of doing the integral. First of all, we'll have to do the boundaries. Now, how are we going to set up the boundaries? As we saw in the previous problem, it's going to be much easier to express the boundaries using spherical coordinates, not rectangular coordinates. Second, the function being integrated. The function being integrated can pretty directly be written in terms of spherical coordinates. And if you don't see that right now, we'll see that in a moment. And also, in terms of doing the integration itself, it is not at all clear how to actually do that integral. So we can certainly hope that once we put it in spherical coordinates, it's going to give us something easier to do. And then, of course, finally, dx, dy, dz is just dv, and we know how to convert that into a spherical integral. Okay, so let's take a look at how this conversion works. So first of all, how can we, sort of the key thing, so we know that this is a solid ball, radius 1. We've previously talked about how do you think of what the boundaries are for that. So for r, for theta, for phi. So it's a solid ball, radius 1. The smallest radius is going to be 0 at the origin. The largest radius is going to be 1. 0 to 1 are your boundaries for r. Next, what about for theta? Well, it's a solid ball, so theta wraps all the way around 0 to 2 pi. And then also, it's a solid ball, so phi goes all the way from top to the bottom, 0 to pi. So those are your boundaries. Next, I'll save the hardest for last. We know how to convert dx, dy, dz. We know that's going to be r squared sine phi, dr, d phi, d theta. That's the formula that we have. Finally, we need to convert our formula in terms of from x, y, z into r theta phi. So for this, we have to be a little bit clever. But how can we convert? What's the easiest way to convert all this in terms of spherical coordinates? Well, we know that x squared plus y squared plus z squared equals r squared. And that's the conversion. So we've got e raised to the r squared raised to the 3/2. R squared to the 3/2, of course, is just r cubed. And there's your conversion. So we've got the boundaries, we've got the function, and we've got the dv all set up in terms of spherical coordinates. And now we can go ahead and do this integral. So first, integrating dr. How do we do it? We do a substitution. So u is going to be r cubed, and then du will be 3r squared dr. So then we just swing the 1/3 around, and now we can reset it up. So doing that, the integral of e to the u, of course, is just going to be e to the u. So then put it back, and you get 1/3 e to the r cubed, with the sine phi coming along for the ride. And we evaluate as r goes from 0 to 1. Next, we do the d phi integral. So, plugging in, you get 1/3 e minus 1 sine phi. Next, we do the d phi integral. So integrating d phi gives you negative cos phi times everything else, which is a constant. And now we have to evaluate as phi goes from 0 to pi. So plugging in pi, you'll get 1. Plugging in 0, you'll get -1. Subtracting and combining constants, that just gives you 2/3 e minus 1. That's all the constants, so integrate d phi, you just get 2/3 e minus 1 times phi, and now evaluate that as phi goes from 0 to 2 pi, and you get 2/3 times e minus 1 times 2 pi, combine it, and you just get 4 pi e minus 1 over 3. So the key with this problem is to recognize from the original problem, recognize that it's a much better idea to do it not in rectangular coordinates as it's given, but to convert it to spherical coordinates. Now, what are the clues to do that? Clue number 1, the integral as it's written, we don't actually know how to do. Clue number 2, the region is a solid ball, so it's a sphere or spherical type thing. Going to be much easier to write down the boundaries using spherical coordinates. In fact, the boundaries all wind up being constants. So, summarize all of these things for spherical coordinates. A little bit on cylindrical, but then also spherical coordinates. So to convert from spherical rectangular and to convert from rectangular to spherical, we have these conversion formulas. And that's the first bit. Second bit is we have the conversion formula for the differential part. So dv is right over here. So dv, which we already knew is dx, dy, dz in rectangular coordinates, we know that in spherical coordinates, it should be written r squared sine phi dr d theta d phi. And when should we be looking to use spherical coordinates? So for the region, or the solid, I should say, it's going to be easier to express the boundaries in spherical coordinates. Also, the function being integrated doesn't look like it can be integrated right now, so it will or might be easier in spherical coordinates. And then also it's actually possible for the function given to write it in spherical coordinates. Give me that.